Today we're going to be talking about rational functions and their models. So we will be graphing. So if you need to get some graph paper, make sure you do so. A rational function is a function represented by one polynomial divided by another polynomial. So to know if something's rational, you must first check if the numerator is a polynomial and the denominator is a polynomial. Remember that polynomials are expressions with whole numbers as the exponents on your variables. The domain of any polynomial would be all reals, except for where the denominator is undefined. So we're going to go through this list, and you're going to help me tell whether these functions are rational or not, and then state the domain of each. So number one, is it a rational function? In other words, is the absolute value of x minus 1 a polynomial? And is x plus 1 a polynomial? The absolute value of x minus 1 is not a polynomial. So this is not a rational function. We could still find the domain. It said the domain is all reals except where our denominator is undefined. So our denominator is x plus 1. So where is x plus 1 not equal to 0? Because if I have 0 in my denominator, it is unexplainable. So subtract 1. X cannot be negative 1 is my domain. Next function, x squared minus x minus 4. And it has no divisor, so we could say over 1. So is x squared minus x minus 4 a polynomial? And is 1 a polynomial? Yes, they both are. So this is a rational function. The domain, I can have a denominator of 1. I don't have any variables down there, so the domain, x, is all reals. Number 3, 4 minus 3 over x plus 1. In order to determine if it's a polynomial, we have to have one numerator over one denominator. So we're going to have to rewrite this. We're going to have to multiply the top and bottom by x plus 1. So this would give me 4x plus 4 minus 3 all over x plus 1. That is 4x plus 1 over x plus 1. Is 4x plus 1 and is x plus 1 polynomials? Yes, they are. So this is a rational function. My domain, again my denominator, x plus 1 cannot be 0. So subtract 1. X cannot be negative 1. Number 4, is x minus 2 and x squared minus 4 polynomial? Yes, so this is a rational function. The domain, x squared minus 4 cannot be 0. Add 4. X squared cannot be 4, square root. X cannot be plus or minus 2. And the last one, number 5 down here, is 2 a polynomial and is x minus 3 a polynomial? Yes, they are. So this also is a rational function. My domain, x minus 3 cannot be 0. Add 3. So x cannot be 3 is my domain. All right. To find the vertical asymptote, that would be the asymptote that goes up and down. It would be our x equals. We would set our denominator equal to 0. That way, we would have our first asymptote. When you're finding horizontal asymptotes, those are y equals. Those are our horizontal lines. It depends on the degrees. If the degree of the numerator is less than the denominator, your asymptote is going to be y equals 0. If the numerator's degree equals the denominator's, your asymptote is going to be y equals a over b. And lastly, if the numerator is greater than that of the degree of the denominator, there is no asymptote. Instead, our asymptote would be considered slanted. It is not horizontal. This is what will be new from Algebra 2. So let's look at each of these situations. All right, here's where the numerator is less than the denominator. Y equals 0 should be our horizontal asymptote. So here on my graph, y equals 0 is my asymptote. My parent function is y equals 1 over x. Or if I want to put it in my x minus h form, it is a times 1 over x minus h plus k. So if I do my parent function table, can I divide by 0? No. So if I put a 1 in there, I would get 1. If I put a 2 in, I would get 1/2. If I put 1/2 in, I would get 2. So I came over here, 1, 1, 2, 1/2, 1/2, 2, drew in my curve. I can't put 0 in, but I can put -1 in, and it will give me -1. -2, -1/2. -1/2, -2. So then I also plotted those points and drew in my curve. Remember that your your vertical asymptote is setting your denominator equal to 0. So this would give me x equals 0. So x equals 0 is right here. Remember that your asymptotes are the lines that your graph never reaches. So my graph keeps approaching each of those, but never touches it. The shape of this blue graph is called a hyperbola. The domain and range are all reals, except for your asymptotes. So in my case, here the domain, well, let's change colors. X cannot be 0. My range, y cannot be 0. Notice how the asymptote matches the domain and the range. Only thing that changes is that it becomes an equal. This was x equals 0. This was y equals 0. Okay? Let's look at the parent function, 1 over x squared. Again, numerator's degree is less than the denominator's, so my horizontal asymptote is going to be y equals 0. So I'm going to highlight that. My vertical asymptote, x squared equals 0. Square root, x still equals 0. Then I make my xy table. Can you put 0 in? No, I can't have a denominator of 0. Can I put 1 in? 1 squared is 1. How about if I put 2 in? 2 squared is 4, so that's 1/4. How about if I put 1/2 in? 1/2 squared is 1/4. 1 divided by 1/4 is 4. So I came here and I plotted 1, 1, 2, 1/4, 1/4, 2. Can't put in 0, but I can put in my negatives. Negative 1. Negative 1 squared is positive 1. Negative 2 squared is positive 4, 1/4. Negative 1/2 squared, positive 1/4. 1 divided by 1/4 is positive 4. So I came over here and plotted them. So it is hyperbola this way in the first and second quadrants. Again, my domain, x cannot equal 0, matches my asymptote except for not equal. But this time, my range, compared to my asymptote, my y's are always above. So it is y is greater than 0. Let's try, oops, sorry. Let's try a few. Write down y equals 1 over x minus 2 plus 1. Does this match the parent function? If I cover up everything except what was done to x, do I have the parent function? Yes, I have 1 over x. So this does match a parent function. So my asymptote is right here. X minus 2 equals 0. Add 2, add 2. X equals 2 is my asymptote. So x equals 2 is my asymptote. So that means my domain, x won't be 2. And remember, when the numerator is less than the denominator, my horizontal asymptote, y equals 0. However, what effect will this plus 1 do? It will take my 0 and move it up 1. So that changes my horizontal asymptote to x equals 1. So my range, y, can't be 1. So now I'm going to plot off of my new xy axis my same parent function values. Y equals 1 over x. 1, 1, 2, 1/2, 1/2, 2. And the negatives. Negative 1, negative 1, negative 2, negative 1/2, negative 1/2, negative 2. So from my asymptotes, 1, 1, 2, 1/2, 1/2, 2. And I'm going to draw in that part of my hyperbola. Then I'm going to do the other side, negative 1, negative 1, from my new origin. Negative 2, negative 1/2. Negative 1/2, negative 2. And draw in that part of the hyperbola. Let's try another one. 1 over x plus 2 plus 3. Does this make a parent function? Yes, 1 over x again. So let's get our asymptotes. X plus 2 equals 0. Subtract 2. X equals negative 2 is my horizontal asymptote. So x equals negative 2. I'm going to draw in that asymptote. Do I have a vertical shift? Yes. So my horizontal asymptote will be y equals 3. So I'm going to draw that one in. So that means my domain, I can have everything except negative 2 because I can't reach this line of negative 2. My range, I can have everything except 3 because I can't reach this line of 3. And now we can do our parent function. 1 over x. 1, 1, 2, 1 half, 1 half, 2. And the negatives. Negative 1, negative 1, negative 2, negative 1 half, negative 1 half, negative 2. So from our asymptote origin, we're going to plot 1, 1, 2, 1 half, 1 half, 2. And we're going to hug our asymptotes. And likewise, negative 1, negative 1, negative 1, negative 1, negative 2, negative 1 half, negative 1 half, negative 2, and hug our asymptotes. When you have something that does not look familiar, that does not look like a parent function, simplify before you start to graph. So 2x plus 1 times x minus 2 over x minus 2 squared. Would you agree with me? These x minus 2's will reduce, and I'll have just one x minus 2 on the bottom. So this actually becomes 2x plus 1 over x minus 2. Now, does that look like a parent function? No, it does not. But notice our hint up here. Use our synthetic division to rewrite it so it's in graphing parent function form. So my divisor, x minus 2. My root there would be 2. So I put that in my divisor box. I have 2, my x, and my 0. Bring down my 2. 2 times 2 is 4. That gives me a 3. Excuse me, it gives me 5. So this is my remainder. This is my x to the 0. So I have x equals 2. So it would be 2 plus 5 over x minus 2 is my y. Now, does this model the parent function? Oh, that didn't work very well. But if I take away my minus 2 and my 2, 5 over x, or 5 times 1 over x, so yes, I do have my parent function. So this is what we're going to use to graph it. So x equals 2 is my asymptote, my vertical one, so x equals 2. My horizontal, y equals 0, but I'm shifting up 2, so y equals 2. Okay, so my domain, x can't be 2. My range, y can't be 2. So my parent function, see if I have room for it. 1, 1, 2, 1/2, 1/2, 2. And my negative 1, negative 1, negative 2, negative 1/2. I now have a multiplier of 5, so I take that times my y's. 5 times 1 is 5. 5 times a half is 5/2. 5 times 2 is 10. 5 times negative 1 is negative 5. 5 times negative half is negative 5/2. So I'm actually going to plot 1, 5 from my new origin. 1, 1, 2, 3, 4, 5. 2, 5/2. 2, 2.5. 1, 2, 1, 2.5. 1/2, 10 is going to be way up there. So I'm still going to hug to my asymptotes. Negative 1, negative 5. Negative 1, negative 5. 2, 3, 4, 5. Negative 2, negative 2.5. Negative 2, negative 2.5. So do you see a multiplier just pulls us further away from our origin? Stretches us further apart, but we still have the same basic graph. Does this model a parent function? Let's see. If I take away my k and my h, do I have 1 over x squared? Yes, I do. So yes, this is a parent function. So again, my denominator, x minus 2 equals 0, gives me an asymptote. Add 2, x equals 2. So I'm going to draw in my asymptote at x equals 2. Y shifted down 1. Y equals negative 1. Now I do my parent function. 1 over x squared. 1, 1, 2, 1/4, 1/2, 4. And the negatives. Negative 1, negative 1, negative 2, positive 1/4, negative 1/2, positive 4. So from my new origin, 1, 1, 2, 4, 1/2, 4. Oops, that was 2 1/4. Let's erase that one. 2 1/4. Negative 1, negative 1. Negative 2, negative 1/4. Negative 1/4, negative 1/2, negative 4. Oops, nope, they weren't negatives, they were positives. Oh, let's try that one again. Negative 1, positive 1. Negative 2, positive 1/4. Negative 1/2, positive 4. There. I do have my hyperbola right beside each other. So now my domain should model that. I still never touched 2, so x can't be 2. My range should be y can't be negative 1, but it is also above negative 1. So y is greater than negative 1. Okay. We'll do these two here yet. Remember to always simplify first. So x squared minus 2x plus 1. That can factor into x and x, factors of 1, 1 and 1, negative and negative, over x minus 1. So x minus 1s would reduce. So I actually have the line y equals x minus 1. So it crosses at negative 1. Up 1, over 1, up 1, over 1, up 1, over 1, down 1, left 1, down 1, left 1. But before I started, I have x can't be 1. So I have to have a hole here at the x is 1. And every other part of my line will be continued. But otherwise, if I had 1, this would not have been explainable, would not have been reducible. So let's try another one. 6x minus 1 over 3x plus 6. Okay, does 6x minus 1 factor? No. So this time, our degree matches numerator and denominator. So how we're going to do it is that we are going to, my asymptote, y equals 6 divide 3, y equals 2 is my horizontal asymptote. My vertical asymptote is still right here. 3x plus 6 equals 0. Subtract 6. 3x equals negative 6. Divide by 3. X equals negative 2. X equals negative 2. This does not model a parent function, so I'm going to have to just pick values into my original function. I cannot pick negative 2, so I have to pick values to the right of negative 2 and to the left of negative 2. What's the value to the right of negative 2? Negative 1 and 0. Let's do those. 6 times negative 1 minus 1 over 3 times negative 1 plus 6. Negative 6 minus 1, negative 3 plus 6, negative 7 thirds. That's negative 2 and 2 thirds. So negative 1, and this is not a parent, so I have to go from my original origin, not a parent function. So use original origin. So negative 1, negative 2 and 2, 1/3. We put in 0. 6 times 0 minus 1 over 3 times 0 6. Negative 1 6th. 0, negative 1/6. And then just hug through those. Okay, let's go left. Left of negative 2, negative 3, negative 4. 6 times negative 3 minus 1 over 3 times negative 3 plus 6. Negative 18 minus 1, negative 9 plus 6. Negative 19 over negative 3. Negative negative makes positive. So 6 and 1/3. Negative 3 for my original origin. Positive 6 and 1/3. Here's 5, 6 and 1/3. Negative 4. 6 times negative 4 minus 1 over 3 times negative 4 plus 6. Negative 24 minus 1, negative 12 plus 6. Negative 25 over negative 6, 4 and 1/6. Negative 1, 2, 3, 4, 1, 2, 3, 4, and 1/6. And hug through those. And we have our hyperbola. So our domain, x, can't be negative 2. Our range, y, can't be 2. I think you have enough to get started on an assignment. Through your assignment, work through only these kinds of graphs.